So what you'll learn in today's class, the following. I'll talk about the diffusion process, processes in bulk and nano. Diffusion process is governed by the well-known Fick's law. Then you'll see all about defects in solids. Then quickly how to distinguish nanomaterials in a more elaborate way, you'll see later. And I'll also tell you about a few recent discoveries related to nanosciences, and then the pedagogy of nanoscience. So this was where we ended the class last week. I said you have the macrostructure. By looking at the material or an object, you make some predictions, but then you can't get deeper information about the electronic processes, etc. Microstructure, of course, is important, but then microstructure at the most can say, yeah, the material that you have is a polycrystalline material, and so you have the problem of grains, grain boundaries. So to that extent, the physical properties will be, altered or affected. So crystal structure is always very important. I keep emphasizing the fact that crystallography plays a crucial role in understanding the materials and material properties, and atomic structure, in correlation to crystal structure is again very important. But then having known about crystal structure and atomic structure, then if you are specifically trying to understand about a given material property, then you have to go and measure those properties, whether they're electrical properties or magnetic properties, as a function of temperature. Otherwise, you won't be able to distinguish between different types of materials exhibiting electrical properties and magnetic properties, right? So if you look at this one, as I mentioned to you, electrical property measurement is a very simple measurement. You take a material and you pass a current. You have a voltage source, and as I told you, if you know the cross-sectional area, you'll be able to find the specific resistance value. And the inverse of resistivity is conductivity. It's a bulk property. And this simple measurement of taking, whether you deal with metals, semiconductors, insulators, semi-metals, or superconductors, the process is passing a current depending on the nature of the material and measuring the voltage drop. Okay, it's as simple as that. But you cannot get complete information about all these different types of systems without measuring sigma, the conductivity, or rho, the electrical resistivity, as a function of temperature. When you do that, this is an extraordinarily simple measurement. All the way from metals, having very high conductivities, to semiconductors, to insulators. You can distinguish between metals, semiconductors, insulators. In between, you have semi-metals and you have superconductors, of course. Highest conductivity is possible. 27 orders of magnitude in terms of the measurement range is possible. I don't think any other technique gives you a possibility of measuring so many orders of magnitude. It's only in the case of electrical resistivity measurement this is possible. Of course, to distinguish between different types of magnetic materials, paramagnetism, diamagnetic material, ferro, ferri, antiferro, you need to measure a property called susceptibility, magnetic susceptibility, as a function of temperature. And magnetic susceptibility again measures over almost 12 orders of magnitude. But electrical property almost double to that, 27 orders of magnitude, and that this simple measurement can distinguish between different types of materials and the electronic process there. And you see, you can scale these conductivities for metals. The conductivities are greater than 10 raised to 5 Siemens per meter. For semiconductors, the conductivity ranges are almost range over 11 orders of magnitude, -6 to 10 to the power of 5 Siemens per meter. Insulators are, non-conductors. So for all practical purposes, the unit of resistivity is ohm meter. The inverse of that is electrical conductivity, which is ohm inverse, meter inverse, and um, the unit is unit of conductivity, electrical conductivity is Siemens per meter. Look, again, just as the way we started looking at macrostructure, microstructure, and like what we have seen in the case of just looking at the material to predict something about the material system. What I've shown here are three pieces of, there could be shiny metal. They're shiny, of course. There could be metals or alloys. This is for sure. Because metals are shiny, and some of the semiconductors also are shiny. Superconducting alloys are shiny, intermetallics are shiny. So if I show you these three pieces and ask you to comment about the electrical conductivity, you won't be able to make any guesses, right? But then if I list all these 5 properties, electrical, magnetic, dielectric, piezoelectric, and superconducting, and if I ask you what out of these 5 properties, or which of these properties these 3 shiny elements may exhibit. So the answer is, you strike off the 3rd point and the 4th point. Dielectric and piezoelectric are struck off, because dielectricity is a property exhibited by insulators. Piezoelectricity is also a property exhibited by insulators, and dielectric property and piezoelectric property, since they're exhibited by insulators, and these don't look like insulators. That's the only thing that we can say. I'll say that yes, these 3 elements or alloys can exhibit good electrical properties. They could be magnetic, they could be superconducting, nothing more than that. Then you go one step ahead and do crystallography, right? I can find out, yeah, this may belong to face-centered cubic lattice. The other one may be a body-centered cubic lattice, but nothing more than that. Of course, you need to know about the crystal structure also. But then I can only say that a particular one of these belongs to one of these phases, as a BCC or FCC or a hexagonal phase. But what about the real, if I ask you to comment about the electrical property? So that's where you have to really go and do measure resistivity as a function of temperature. And you know what happens? It turns out that the first one that you see here turns out to be platinum, which is a noble metal with, if you see platinum, you always see a linear decrease in electrical resistivity followed by saturation at lower temperatures. And this rho naught represents the residual resistivity. Higher the rho naught, higher the impurity concentration in the element or any material. So basically, you can also have a plot where if rho naught is 0, if you take a pure platinum, it shows linear decrease in the resistivity as a function of temperature, and rho naught could be almost 0, which indicates that's a pure form of platinum. You see, so much you can understand. Unless you do rho versus T, you won't be able to find out the first one there is actually a metal. And how do you know it's platinum? You will know from X-ray diffraction and also some elemental analysis. The second one here turns out to be germanium, and germanium, the rho versus T behavior is that. It's a typical behavior for a semiconductor. And the third one turns out to be lead. And you see the normal state resistivity is again a linear decrease in rho as a function of T, just as what you see in the case of a normal metal, but at a certain temperature and below, you see the superconducting transition happening. Tc goes to 0, that's called the superconducting transition temperature. You see how by just looking at them, you won't be able to predict all these properties unless you go and do those measurements. We won't be able to say the first one is platinum, the second one is germanium, the third one is lead. So this is where the physical property measurements, especially the electrical and magnetic property measurements, as a function of temperature, are always very crucial. Okay. So again, going back to the polycrystalline material, all right, again, uh, this is what I mentioned yesterday. You take this semiconductor in a crystalline form and a polycrystalline form, the order of resistivity can change because the basic building block is the same, whether you get this semiconductor in a polycrystalline form or a single crystalline form. So the basic building blocks are the same. That is the unit cell, right? But then the long range correlations are affected if you get it in a single crystalline form, polycrystalline form, and amorphous form. That's where your rho versus T behavior may be the same, but the magnitude of rho can change of all these systems if they're obtained in different crystalline forms. So again, polycrystallinity, you have grains and grain boundaries. Each grain is crystalline. This is how the unit cells are perfectly periodically arranged inside a grain. The neighboring grain is also crystalline, but you have a defect that is called the grain boundary. Okay, and when you use the top-down method by using by crushing a polycrystalline material or a crystalline material, you break the material at grain boundaries, and imagine if this is a nanocrystalline nanoparticle that you get it from by crushing this polycrystalline material. Let's say the particle size is 8 nanometers, and there are large number of these particles you obtain from a single grain. So you expect a polycrystalline material to be always crystalline. Let's look at the diffusion process. The bulk material itself, how is it prepared? Suppose we are interested in making a compound called MgAl2O4. It has a very interesting properties, magnesium aluminum oxide. But let's look at how magnesium oxide is prepared. Magnesium aluminum oxide is prepared. This is done by what is called the solid state reaction method. You start with the metallic magnesium and aluminum and oxidize the elements. But the easiest way is to start with the constituents of magnesium and aluminum. The constituents that are readily available and are also stable. The readily available constituents of magnesium and aluminum are magnesium oxide and aluminum oxide, MgO and Al2O3. So it's like you're bringing a piece of magnesium oxide and a piece of aluminum oxide, and you want the reaction to happen. Of course, you go through the phase diagrams and make sure that a reaction is possible between magnesium oxide and aluminum dioxide to realize the new phase called MgAl2O4. So for that, high temperature reaction is always required. No, otherwise you can't form the new phases because you break the bonds in these individual compounds, and then the new phase forms. All right. So now imagine if I'm taking a block of let's say I'm taking a block of magnesium oxide, a block of aluminum oxide, and these two blocks are connected at this interface, and then you want a reaction to happen at the interface. It's fine, it's no problem. But the only interface available for the individual species to diffuse around is this interface alone. That's interface. So any new phase forming, you'll only see at that interface, right? And phase formation also is temperature dependent. So because you need to heat the materials, these two materials, the combination to high temperature, One may be having a higher melting point, the other may be having a low melting point. Of course, for polycrystalline material formation, you need to go up to the level of the melting point, but then somewhere close to 92% of the melting point is fine. But then the 92% of melting point of aluminum oxide is much higher compared to the 92% of melting point of the other compound, let's say AB. So in that case, you would always go below the melting point of the lower melting point of one of these materials. So that can complicate issues because the diffusion from the other material may not be very effective. So diffusion process is a temperature dependent process. And in solids, the diffusion is absolutely slow. So imagine if okay, so look, so for this new phase to form, the magnesium ions diffuse to this side and aluminum ions diffuse from aluminum oxide side to this side. Aluminum valence state is 3 plus, magnesium valence state is 2 plus. So for every 2 aluminum 3 plus ions, 3 magnesium 2 plus ions move to the other side. And then you're also providing oxygen during this process. This is a nucleation of the new phase, magnesium aluminum oxide. Okay. But how slow it is, and because you're breaking these individual, or by providing high temperature, right? You're sort of providing enough thermal energy for atoms to relax from their lattice positions. Atoms also form based on the available crystallographic planes. See, you have magnesium oxide, you have aluminum oxide, you have the new compound called magnesium aluminum oxide, and this new compound might find already existing crystallographic planes suitable to grow its phase. Because for every growth of a phase, you need a nucleation site. And these nucleation sites may be already inbuilt either in magnesium oxide or aluminum oxide. Okay, so that's how the product forms. But talking about, this is how finally the polycrystalline material forms. Polycrystalline material, which is heated to lower temperatures. You see still the grain growth is not perfect. And then when you go to the highest possible temperature, you see the grains growing bigger, but this also happens at a cost of losing the material with all these voids. But the basic concept of diffusion in solids is, the diffusion of ions in solids is extremely slow. And diffusion can happen by thermal gradient, by providing a potential gradient under the influence of magnetic fields. Anything is possible, right? All these different mechanisms can lead to diffusion. What is the fastest way of diffusion? I'm simply sitting in my room and somebody enters into my room and takes a small spray bottle and presses it there. A few ml of this, gaseous molecules of this spray that jets out through that tiny hole. The very next second, in milliseconds or microseconds, I'll be able to smell it, here, sitting 3 meters away. That's the fastest. Now, what about diffusion in liquid? Suppose I have a clean liquid like this, okay? And then, so let me show you. You all must have done this interesting experiment of dropping, let's say, a drop of, see that? That's a beautiful process of diffusion through a liquid. It happens, but not as fast as what happens in the case of a solid. It's fine. Okay. Now, when it comes to diffusion in a solid, if you actually calculate the diffusion lengths, these are anywhere from nanometers to microns. All this depends on the temperature. And if you want to have a reaction to happen at room temperature, it's impossible. Probably one has to wait millions of years. If this block is, say, 1 centimeter and 1 centimeter on that side, if for these species to diffuse, it will take thousands of years. So that's where high temperature reactions are required. But even when you provide high temperature, the only interface that you have between these two is only this one. So see, that graded, the colored region is where the new phase forms. So it's exactly so you're provided one nucleation site, only one nucleation site between this one. So this one now has completely diffused. Still you need some shaking up and all that. So that's some kind of mechanical force. Okay. So we have provided for diffusion to happen only at that interface, this interface, right? So how do I hasten up this process? I can hasten up this process from this scenario by, cutting down the size of this block into smaller pieces, and this block into smaller pieces, right? Because here you see the reaction interface is only that one, only that one. Now the idea is to increase the number of nucleation sites. How can I do that? Here it's only one. That takes a lot of time for all these pieces to diffuse. So what I do is I cut this down to smaller pieces, so micron size pieces. Normally, if you take a block of any ceramic material, if you just subject it to mechanical attrition, it takes about it takes about a few hours to get down to smaller particle sizes. But these particle sizes by mechanical attrition are anywhere from 25 to 50 to 75 microns, which is fine, which is much smaller than the bulk material size. Then we need to mix up these two in such a way that, now you can see how many interfaces are there. You have large number of interfaces, isn't it? I've created so many interfaces that I can have this reaction to happen at a large number of these interfaces. All those green indications are new interface. See, from one interface, I could increase the number of interfaces. And the good thing is, so this leads to the nucleation, leading to the nucleation of certain number of these smaller particles to agglomerate into one bigger grain, the neighbor grain, and the grain. But these grain boundaries are inevitable because these are the boundaries that that also have lower energy to form. So unless you surmount the energy of those grain boundaries, they're always stabilized. That's where if you want to completely eliminate them, you need to go for a single crystal growth. Otherwise, grain boundaries are always there. Now imagine, how do I further increase this reaction between these micron-sized particles? Now, if these micron-sized particles are now brought down to nano size, right? Sizes of the order of few nanometers, right? Now, that means each of those particles is further subdivided into smaller particles. Then you create more number of nucleation sites, right? Millions more. And then so the two things happen when you cut down the size. When you cut down the size, you're increasing the surface area and also the surface energy. These two are very important factors. That means what? A bulk material, when it is in bulk form, it has a surface energy. So you're providing high temperature to increase that surface energy so that diffusion happens, right? But in the case of the same bulk material cut down in size, what I have done is I've increased the surface area of these particles, and with increase in surface area, the surface energy is also increased, because you can do this simple calculation. You take say 10 micron sphere of any material, and you calculate, let's say this 10 micron sphere is made up of uh, atoms atoms whose diameter is say 2 angstroms. So you know the atomic size, and then these 2 angstrom atoms make up this 10 micron spherical particle. Okay. Now you cut down this 10 micron spherical particle down to smaller particles. Let's say ideally you get spherical particles of smaller size, but then you could cut down this 10 micron diameter particle to smaller particles of 10 nanometer size. Now first you try to do a calculation as to how many 10 nanometer particles could be obtained from this 10 micron bulk material. That itself will be, that number will be staggeringly high. And if you calculate the number of surface atoms in the case of the 10 micron bulk sphere and a 10 nanometer sphere of the same material, then you will see the difference. The number of surface atoms in the case of nanophase, in bulk, it could be 1 to 2%. In the case of nanophase of the same material obtained in bulk form, nanoform, the number of surface atoms could be anywhere from 5 to 40%. In some cases, 50% of the atoms could be surface atoms. So the more number of surface atoms, the more reactivity. So nanoparticles become very reactive. So the temperature that is required for a reaction to happen between two bulk components, like say A and B here, magnesium oxide and aluminum oxide, same magnesium oxide and aluminum oxide, when they're made to react in the smaller particle form, micron sized particle form, or even nano sized particle form, the reactivity, so the amount of temperature required for the reaction to happen will decrease drastically. So there are some cases where ceramic particles can be fused almost close to room temperature when you start with nanoparticles because of the enormous increase in the surface energy, right? Okay. So, and this concept that I mentioned here, reducing the particles, is normally how ceramic objects are made, not by making a reaction happen between two solid bodies, but the ultimate thing is going to nanophase, right? The much smaller particles is also a process that is used in thin film growth. So you take a polycrystalline material. Well, when I say that you make the particle size lower to the nanoscale regime, we are taking the particles down to very small sizes. So it's the same concept that can be used to explain the thin film growth process. So if I take a bulk polycrystalline material with all the grains and grain boundaries, now I can use it as a target in a thin film growth method. Now you break the target by some means. There are various ways in which these targets can be broken by, mostly by plasmas or lasers or X-rays. Now you're atomizing the target. So you have a target with Mg-Al2O4 composition. You're completely atomizing it, and all these atoms with the same compositional stoichiometry, they're made to recombine on a substrate. Now imagine, now from micron size to nano size to making the individual atoms to react. That's why the thin film growth process is so fast. If I take say a 1 week to prepare Mg-Al2O4 bulk material, okay, when I use it to grow a high quality single crystalline thin film, because I'm again breaking up Mg-Al2O4 into, I'm atomizing it, and I'm making almost individual atoms or small clusters to react. That reaction is so fast that I get a crystalline form of Mg-Al2O4 in thin film form in just a few minutes. I can get on a 1 centimeter square area, a highly crystalline Mg-Al2O4 in 20 minutes to half an hour of a thickness of about 200 to 300 nanometers. But a single crystal growth of MgL2O4, again, I have to take it to its melting point, a slow cool it. Then after a few days, I get a bulk crystalline MgL2O4. Okay, so that's to diffusion. You know, I keep mentioning this. One can always control these grain boundaries, and you have this beautiful field called grain boundary physics. So extension of perfect crystallographic structure in 3 microscopic dimensions: single crystalline, epitaxial thin films, and then you see this is a crystal, a thin film, and a polycrystal. They're all examples of all 3 forms of materials. Presence of defects in crystals, nanomaterials, and thin films can influence physical properties, their chemical reactivity, chemical, electrical conduction, mechanical behavior, reflectivity. All these properties are affected because of the presence of defects. Dislocations and vacancies, of course, you have these line defects, edge and screw dislocations, and these bear a definite crystallographic relation with the lattice. Elimination is possible. Grain boundaries cannot be completely eliminated, but you can reduce the grain boundary width. Vacancies are, of course, point defects, Schottky and Frenkel defects. Vacancies are an integral part of any crystal. That's why we don't have perfect crystals, and one can estimate the fraction of vacancies formed given the formation energy of these vacancies. Yeah, just an example of edge dislocation. We are really not interested in edge dislocations when you're talking about nanoscale materials. Grain boundaries and defects, more so in the case of bulk polycrystalline systems. You have other stacking faults in materials. So a vacancy is a Schottky defect, right? And you have a missing atom, which is a Frenkel defect, interstitial position. So these are all the atomic positions, and you have you have an atom that can move to a vacant position, and atoms also can sort of diffuse this way in the lattice. Because you see, if you take any lattice, a large part of the lattice is vacant. You can calculate it for a simple cubic lattice, a face-centered lattice, and a body-centered cubic lattice. There are some lattices where the packing fraction is very high, but otherwise, lattice has a lot of space for these atoms to diffuse around. Okay, so this is an example of vacancy diffusion, interstitial diffusion. So because there's a vacancy, when you provide thermal energy, you can start seeing this atom moving around. Okay, and when atoms start diffusing in a lattice, you have atoms or ions. You talk about ionic conductivity. All right. Exactly. So we normally talk about the rate of diffusion. Diffusion is a time-dependent process. I gave you an example of how fast diffusion happens by the gaseous medium and liquids. Diffusion is a process is extremely slow in solids because the solid is already formed, and the time scales involved for diffusion in solids is extremely small. So the diffusion kinetics of nanophase material and bulk material are totally different. So the reactions can happen much faster in nanoscale. How fast the diffusion occurs or mass transfer occurs, this is expressed as the diffusion flux. J defined as the mass or the number of atoms, M diffusing through and perpendicular to a unit cross-sectional area of solid per unit time. In mathematical form, it is given as J is equal to M by AT. And you have this well-known fixed first law of diffusion, which is J is equal to minus d dou C by dou x. Dou C by dou x is a concentration gradient. J is expressed in units of atoms per meter square second. D is the diffusion coefficient, diffusion constant, which is specific to a given material. You also have Fick's second law. Fick's second law is a rate determining equation. It says what temperatures are required in order for a given reaction to happen, right? That is dou C by dou T is equal to D dou square C by dou x square. And this can, the Fick's first law also can be written in the form of, uh, divergence form. J is equal to D del C. Okay. Just to give you some examples, diffusion coefficients as a function of reciprocal temperatures. You see how carbon diffuses in gamma Fe, how aluminum diffuses in aluminum. So even in some cases, there'll be self-diffusion at room temperature and at elevated temperatures. Okay, copper in copper, iron in alpha Fe. And you get all this standard data from all these handbooks, all these reference books. It shows the diffusing species, the host metal, D naught, because your D is equal to D naught exponential minus EA by KBT. EA is the activation energy of diffusion. This is the pre-exponential factor. And activation energy, you can get it in kilojoules per mole or electron volts per mole, and the temperatures, right? And the calculated values of diffusion in meter squares per second, right? In solids, the diffusion coefficients, diffusion lengths are very small. This is just to show you that if you have a block of copper and nickel, you see if there is only one interface, the diffusion of copper and nickel atoms happen within that couple, that's only one interface. This is how the concentration profiles as a function of position can be shown of copper and nickel. But then when I enhance it into multiple reaction between smaller particles, you increase the diffusion process, and so you make the reaction to happen. That's why nanophase compounds can be, the diffusion is more. See, even in a bulk material, there is surface diffusion and there is volume diffusion. There is also grain boundary diffusion. The surface diffusion is different from the volume diffusion because surface atoms are normally loosely bound. But when you go to the nanophase, I have asked you to do this simple calculation. By virtue of having more number of surface atoms, the diffusion is much faster in the case of nanophase. So you can also do a simple calculation, right? I'm asking here to calculate, if you have a plate of iron that is exposed to a carburizing atmosphere on one side and a decarburizing atmosphere on the other side at 700 degrees centigrade, if a steady state condition is achieved, how do you calculate J of carbon through the plate if the concentration of carbon at positions 5 and 10 millimeters beneath the carburizing surface are 1.2 and 0.8 kilograms per meter cube, respectively? Assume a diffusion coefficient of 3 into 10 raised to minus 11 meter squares per second at this temperature. It's very easy to do. This is a equation, J is equal to minus D. These are the concentration gradients of A and B and the positions of A and B, right? It's a very simple way of getting J value, right? Okay. So look, in a solid, if you want to bring in physical property changes, all these open circles are the lattice positions. These are called the lattice atoms or lattice positions. When you substitute an atom, lattice atom, by a foreign element, for example, a silicon atom in silicon crystal replaced by phosphorus, the phosphorus brings in addition an electron because it brings 5 electrons. Normal silicon bonds with 4 neighboring silicon atoms by sharing 4 electrons, right, forming a covalent bond. So if I replace that silicon by phosphorus, it also brings 4 electrons, but it has an additional electron that can be given to the lattice. That is meant by doping. But that electron makes a mobility of silicon to change, the diffusivity of silicon that leading to better conductivity. But for that to happen, the phosphorus atom has to replace the substitutional atom. It can't go and sit in the interstitial position and still have the same effect of giving this additional electron to the lattice. That is what is meant by substitutional impurity. But before I go there, so this is the vacancy that is called the Schottky defect. Interstitial, where an atom has been moved to a non-atomic position, right? That is, these are the atomic positions, but an atom completely missing is Schottky defect, but an atom that has moved to a non-atomic position is called an interstitial. That is called a Frankel defect. We can substitute the atoms present in the lattice by smaller or larger ions or atoms, and of course there is a limit to which an bigger atom can replace the existing atom of a certain size, or a smaller atom can replace it. So when a smaller atom replaces the lattice atom, it compresses the lattice, and in this case, it expands the lattice. How do we know? This is a very local phenomenon. There's one atom here, there's also one atom here. Also, when you dope a material, the distribution of these atoms inside the solid, we don't have a control on that. It's just a statistical distribution. But when you subject this material before and after doping, when you're seeing these expansions and contractions of certain volumes in the lattice, you can get an overall information from diffraction, electron diffraction or X-ray diffraction. That's why to know that a lattice atom is replaced, you need to do crystallography. Yeah, this is about the substitutional atoms. And you also have what are called Frankel pair defects, right? So an interstitial atom there and a vacancy there can form what is called a pair, Frankel pair. Today, again, we may think that just as grain boundaries are detrimental to physical properties, but I also mentioned that controlled grain boundaries can have many positive implications. Similarly, controlled crystal defects play a very significant role in many applications. First of all, um, uh, these substitutional atoms also are defects inside a solid. I'm bringing in a foreign element. So these elements that are doped into a solid can bring about changes in conductivity, can bring about changes in optical properties, can bring about changes in magnetic properties. That's a power of doping. And in silicon or any of these semiconductors, when you're talking about changes in electrical properties by almost 3 to 4 orders of magnitude, you're only talking about replacing, or the dopant concentration is of the order of 3 to 5 atom%. It's very small. But these small percentage of dopants can cause such a big change in the physical properties. But this is all in bulk. Huh? We're still not talking nothing about nanophase. What is the effect of these dopants in the nanophase and all that? That becomes, you know, much more interesting. So defects also can change the color of solids, because these defects can create additional absorption and emission levels, leading to changes in the coloration of these crystals and formation of these Frankel pairs. So today we talk, this is an example of how color centers, these are called color centers, can render crystals colorful because of the defects present. These could be point defects or even substitutional atoms. The Frankel pairs, again, if you control these defects, today it's all about creating these defects called NV centers. That means I replace this is diamond. Diamond is made up of carbon. You replace carbon by boron. You tune the electrical property of diamond. An insulating diamond becomes semiconducting, metallic, and even it shows superconductivity. Similarly, if I replace carbon by nitrogen, nitrogen forms what is called an NV center. And these NV centers are required for fabricating qubits, quantum bits, for quantum computing. And you also have NV center based magnetometry for sensitive magnetic sensing. You see, all that because you create and control those defects at the atomic level. Yeah, I've already mentioned this. So even though presence of defects is defects influence the physical properties, but you certainly can use them for color tuning and applications where you use them for quantum computing and magnetometry, etc. So advanced materials and nanotechnology, if you see all aspects of functional properties of materials in nanoform, again, what all you learn in the bulk aspects of semiconductors, magnetic materials, ferroelectrics, thermoelectrics, photovoltaics, what happens when size reduction happens? So the device aspects at nanoscale, 2D systems are very essential these days to understand the processes. Nanostructured surface coatings, hard coatings, hydrophilic and hydrophobic coatings. These are all the terminologies that are used in nanoscience and technology. Materials for biosensors, quantum dots for biological marking, biocompatible coatings, spintronics, where one uses the spin degree of freedom of an electron. Normally, the charge degree of electron has 2 degrees of freedom, spin and charge. In electronics, we use only the charge degree of freedom. But how about using the spin degree of freedom for various applications? The physics of utilizing spin degree of freedom is called spintronics. Then you have nano electromechanical systems, single electron transistors, positioners. The list is endless. And materials and device aspects of bulk and nanoscale and electronic materials. And you have these interesting fields like nanophotonics, band gap engineering, solar energy harvesting, quantum dots in solar materials. You see, so many things now come in, and they're all, find useful applications of materials, both in the nanoform and in bulk form. This is a very exciting chart provided by Richard Feynman in 1964. This is called Feynman's distance perspective. He gave all this in meters. We have reproduced it in a nice graphical way from his original paper. 10 raised to 27 meters, edge of universe, 10 raised to 24 meters to a galaxy, and so on. 10 raised to 12 meters to sun, to the sun. Because this is not the radius of Pluto, it's radius of the orbit of Pluto. And height of a child in 1 meter. A salt grain 10 raised to minus 3 meters, 10 raised to minus 9. Nanoscale objects, viruses, and all that is in the nanoscale falls in this scale. You see, it's nearly 34 orders of magnitude change in the so-called length perspective. So if you take a semiconductor, if you go on reducing its size, what happens is size reduction leads to, you go down to the de Broglie wavelength limits. Okay, you start seeing this very interesting macroscopic behavior, new exciting physics, quantum Hall effect, conductance quantization, and then you reach this level of single electron transistors. Okay, so single electron transistors are already fabricated using nanowires. Similarly, you take a ferromagnet, the ferromagnetism that you learn at the school and college level. If I give you a ferromagnet, how do you quantify that it's a ferromagnet? It's you do an M versus H curve or a B versus H curve. It shows this hysteresis loop. There's a magnetic saturation that happens in the case of ferromagnet. There's a coercive field and also a retentive field, standard M versus H or B versus H curve. But, interestingly, the physics that we learn in the school and college level, all that changes with size reduction. You start seeing this new phenomenon called the GMR physics, giant magnetoresistance at critical lengths, because this doesn't happen in single magnetic materials. You need to have multiple layers, magnetic layers separated by non-magnetic layers, and leading to this exciting physics of giant magnetoresistance and the devices that can be fabricated using that concept. Okay, then you go down to the superparamagnetism state. So below a certain level, you come down to the level of a few nanometers of the same ferromagnet. What happens? The ferromagnet doesn't act as a ferromagnet anymore. It starts showing properties called superparamagnetism. It's amazing, right? So all these ensemble of particles, each particle is still ferromagnetic in its nanoscale, but the ensemble, all these particles put together, it behaves like a paramagnet, random orientation of spins. And materials in superparamagnetic state have lots of applications in data storage, because these systems have very low coercivity or sometimes zero coercivity. Superparamagnetism finds wonderful applications in medical field. Say, for example, we have managed to make these. See, these are the magnetic nanoparticles, all suspended in fluid. Okay, and these particles are hanging around for many years, and of course, this is called the magnetic fluid. Okay, it has magnetic nanoparticles of 20 nanometers in size, and you also have see a clear fluid, but you have some magnetic nanoparticles at the bottom. But they're all settled down to the bottom. Now, when I shake it up, you see that they start settling down after some time. All these nanoparticles. Okay. Lots of wonderful applications of these nanoparticles. So the nanoform, I defined this earlier. Nanomaterials are those that have feature sizes within 1 to 100 nanometers. Large surface to volume ratio, and they also start showing these quantum effects. And I also said that the sanctity of using this range is within this range, you start seeing physical property changes of semiconductors, metals, and alloys. So based on the shapes and structures, nanomaterials are divided into basically 3 forms. The 2D nanomaterials, these are called the quantum wells. The one-dimensional nanomaterials, examples of nanotubes, nanowires, nanofibers, and the zero-dimensional nanoclusters, nanoparticles. Zero-dimensional nanoform is examples of nanoclusters and nanodots. See, the 2-dimensional system is a thin sheet. A 1-dimensional system is a rod, nanorod, and a 0-dimensional system is a tiny particle where all 3 dimensions are within 1 to 100 nanometers. You'll see the more elaborate description in the later classes, but in simple terms, in the 2-dimensional form, if the material attains what is called a quantum confinement, then you call it a quantum well. Then similarly, the one-dimensional nanomaterials can be called quantum wires, and the zero-dimensional particles could be uh, termed as quantum dots, provided in this reduced form of 2D, 1D, and zero-dimensional systems, they start showing those quantum effects. Otherwise, it remains as a two-dimensional material, one-dimensional material, and a zero-dimensional material. But this two-dimensional material also shows the quantum effect. It's called a quantum well. Then a quantum 1D quantum wire and a zero-dimensional quantum particle or a quantum well. Yeah, a polycrystalline material, a two-dimensional nanoform. Examples are ultra-thin films. These are quantum wells. These can be grown using many of the thin film growth techniques: physical vapor deposition, chemical vapor deposition. You know how to grow a single crystal. I told you, these are complex methods, Czechoslovakia and all. Polycrystalline materials are easy to make using a lab-made furnace. The one-dimensional systems, nanofilaments, nanorods, nanofibers, okay, can be prepared using thin film growth methods as well as many chemical methods. The zero-dimensional form of nanoform is nanoclusters, nanodots, nanocubes, and be lab made by, you can synthesize them by chemical methods. You can also get them using thin film growth methods. So all three forms, 2D, 1D, and zero-dimensional forms can be grown by chemical methods, not a problem. Chemical methods as well as the conventional thin film growth methods, physical vapor deposition and chemical vapor deposition. So, the way, so when quantum effects set in, they're called 2D quantum systems, 1D quantum systems, and zero-dimensional quantum systems. The broader definition is materials that exhibit strong electronic correlations, superconducting, magnetic order, or materials whose electronic properties are linked to the non-generic quantum effects such as topological insulators, the Dirac electron systems such as graphene, as well as systems whose collective properties are governed by genuine quantum behavior such as ultra cold atoms, cold excitrons, polaritrons, and so on. The science of these various systems is very vast. And the common thread in the study of quantum materials is, of course, the concept of emergence. And if you look at this chart, in the olden days, material systems measured in small scale, submicron scale, and technology, these two are two circles uh, separated from each other, but now there's a great overlap. Okay, that's how science progresses. You find new methods, new phenomenology, new applications. Then you start saying that, okay, all that science I know about low dimension systems, I can put them in useful applications. What are they? You learn about the physics of low dimension systems, quantum confinement, quantum mechanical tunneling, and you have these quantum wires, GMR devices, ferrofluids, nanocoatings, single electron transistors, bio-NEMs, and then you see the wonderful phenomena here: quantum Hall effect, scanning probe microscope. Again, a microscope called STM, scanning tunneling microscope, that has evolved by using a simple phenomenon called quantum mechanical tunneling. So nanotechnology can be divided into two categories. You have solid state nanotechnology, which is based on thin films, where you talk about self-assembled nanostructures, multi-layers. Then you grow these thin films and fabricate devices, nanoscale devices, right? And then you have liquid phase nanotechnology, where nanoparticles, colloids, mostly it involves uh, preparation of these particles by standard chemical methods. Yeah, just to remind you of the slide I showed you about the visionary talk of Albert Einstein and Richard Feynman. In 2008, Richard Feynman talked about manipulating atoms. And in 2018, these three scientists received a Nobel Prize for their invention of what is called optical tweezers, with which atoms can be held and manipulated. So this has a great significance in terms of atomic manipulation of atoms. It has such a great significance. And in 2016, Nobel Prize went to the theoretical discoveries of topological phases, right? Topological phases of matter, these three scientists. And in 2014, the Nobel Prize went to the three Japanese scientists. I mentioned this in the last class also. This invention also has something to do with nanotechnology, because these junctions that give rise to blue and ultimately white emission use all these very complex quantum well structures. You need extremely precise growth mechanism to grow all these layers. And then you're seeing the revolution in using white LEDs today in terms of power consumption. So 2007 Nobel Prize went to the discovery of giant magnetoresistance, GMR, to Albert Fert and Peter Grunberg. It's all about their technology now goes into the read and write heads. So we want smaller and smaller devices, but more information to be kept. And look, this whole functioning of hard drive is always wonderful. You have a motor that drives this drive at anywhere from 7,000 to 15,000 RPM. And then there's a casing here. This is the read and write head. Today's read and write heads are very small, nanoscale. And that's the reason why you're able to pack more and more information on the medium there. If you make a size comparison of human hair, 70 microns, the read and write heads are at 49 nanometers, right? As I told you, you can still go down to lower sizes, but the problem is the quantum effects that set in, because these are all not single materials. These are all complex, multiple layers of these layers that give rise to this wonderful property called GMR, giant magnetoresistance. So those layers look like that, and these are grown, and they should see the layer thickness is 5 to 10 nanometers here, the brighter one, and the darker one is 1 to 2 nanometers. You see the precision with which these layers should be grown, and the characterization that goes into making sure that yes, these layers are perfectly good for device fabrication, and then fabricate a device. This is very interesting. This is how science moves and technology moves. It's all about basic science and how you reach on the other side for technological innovations. But before you achieve technology, a lot of scientific work has to be done. So in 1984, so we're talking about how the reading and writing is done, and then we're able to pack more and more information. In 1984, see what you're seeing here is a 1 inch square of the magnetic disk. Okay. Now, nearly 30 years back, the writing head was made of an inductive write head. It used to be bulky. Imagine the paper on which we write on, right? On this paper, the notes that you take with a ballpoint pen, right? Now I'm using this pen with a thick tip because I want to draw those thicker lines so that it's clearly visible to you. But while writing your notes, you don't want to use this marker pen with such a thick tip. Now imagine if the ballpoint pen tip its size increases by 25,000 times, or it's as big as let's say this broad tip like this. Yeah, how many letters you can write on your page? Not many. Same thing happened here. So the right head was so bulky And also in those days, the movement was also not so um, precise in the sense, in terms of moving from one point to the other, it's precise, but finer movements could not be achieved. So now there's a lot of development on the using piezo materials to achieve even angstrom level movement of tips along the X, Y, and Z directions, right? So this is an inductive head, and those black regions are the regions where information was stored. Okay, those are the black regions where information is stored. Now, the point is, so while when the head moved from this position to the other, a lot of this area it remained unused. So that's why you had in 1984 0.04 gigabytes per inch square. And in 1990, even the imaging process has improved. And you see, these are the magnetic domains where information was stored. And you see more number of domains could be written on the same 1 inch square of the area of the tape. So it has gone from 0.04 to 0.1 GB per inch square. But you see what happened in 2004. It's 50 gigabytes per inch square. And you see how many of those magnetic pixels, so to say, could be packed into a 1 inch square of the given area of the recording medium. This is amazing. You see the progress from 1984 to 2005. There's a quantum jump, and in 2015 itself, we reached 1 terabyte per inch square, and theoretically, one can pack 1.3 TB per inch square before these magnetic domains start interfering with each other. So that's the limit. So it's not just about reducing the size of the read and write head or write head. So when you can write, you can also read, right? But it's all about how small you can write. We have already achieved that. That's the reason why you have new processes, new materials that are worked out as to how to improve the storage efficiency. Are there other systems? There are what are called phase change memories that are used in a I won't say big way. There's a lot of research going on phase change memories, and that could be the next generation of memory storage could be done by phase change memories along with the existing technologies. Okay, that's what it is. I've shown it already. If you look at this one, IBM researchers created world's smallest 3D map. And what you see here is, this is, it looks like a normal a picture of a world map that you hang on the wall in the form of a framed picture or a calendar. But to look at the size, here it's 2 microns. So you can imagine this is 22 microns by 11 microns length and width, so small. So how can you write such small on such small areas? By using tiny tips. So what you read here is a tiny silicon tip with a sharp apex, 100,000 times, 1 lakh times smaller than a sharpened pencil, to create patterns as small as 50 nanometers, right? So it is possible. Now, this now today we can create these small, tiny structures. Again, if you see the scale here, 2 microns, you can imagine what would be the size of that tip. So you can create those nanoscale tips, and for and you can use these nanoscale tips in many devices, including scanning tunneling microscope, atomic force microscope, etc. So I'll stop there.